Good morning, everybody. My name is CH Vinay Bharadwaj and I am from EEE first year of section A. Today I am going to explain about mass PPT and my topic is about on skew symmetric differentiation matrices. Okay, on skew symmetric differentiation matrices. First of all, let's get a little bit introduction about our topic. The theory of finite difference methods for discretized partial differential equations is mature and well understood. The mainstay of numerous computational algorithms for the past century. It is a sobering fact, however, that even in its basic linear setting, this theory is incomplete. The theme of this paper is an interesting lacuna in the classical theory. A good starting point is the convection diffusion equation. Bijang 2004, Morton 1996 in a univariate setting, and this is the equation accompanied by an initial condition for t is equals to 0 and Dirichlet boundary conditions at x is equals to 0 and x is equals to 1 when the average transport velocity v is a given smooth function. The equation 1.1 is important because it's multivariate generalization, and this is the equation is a model for transport phenomena combination diffusive and convective process, a powerful means to solve easily extended to a multivariate setting is through an exponential splitting method. Its simplest manifestation, the strange splitting, approximates by the time stepping scheme, and this is the equation. Next one, the method is second order in time, therefore it makes sense to discretize in space to a similar order. This is a case with the familiar differentiation matrices. Now there is a matrices given on the slide, and this is a case with a familiar differentiation matrices. Okay, the above matrices is a case with a familiar differentiation matrices. Next point, we can easily generate skew symmetric matrices of an order. Yes, we can easily generate skew symmetric matrices of an order. For example, see, there is an equation. By this, we can easily generate a skew symmetric matrices. Next point, where delta x is equals to 1 by m represents a fourth order scheme once we wrap around boundaries, that is, identify m with m mod m, the outcome is the skew symmetric banded circulant. See, the above matrices shows that where triangle x where triangle x is equals to 1 by m represents a fourth order scheme. Once we wrap around boundaries, that is, I mean, once we identify m with m mod m. Understood? Identifying m with m mod m. I mean m mod capital M. The outcome is the skew symmetric banded circlet. And next, see, here is an matrices given on the slide. Next point, given the generalizing the non-equidistant approach of section 4 to high orders is far from simple. It seems that not methodology to construct high order skew symmetric differentiation matrices D1 is presently available. Okay, D1 is presently available. And next point, on stability on skew symmetric. Okay, the topic is now about on stability and skew symmetric. First point, let u be a smooth function. Okay, let u be a smooth function for x belongs to open square bracket 0 comma 1 close square bracket. Set um is equals to u of m triangle x close bracket comma u comma m is equals to u comma open bracket m triangle x close bracket. Okay, for m is equals to 0 comma 1 comma 2 comma 3 comma etc so on comma m plus 1, where triangle x is equals to 1 by bracket of m plus 1 close bracket, and consider the approximation. And here is the equation given on this slide. Okay, and the next point is 1. The Price differentiation matrix originates in spectral methods where it denotes an exact linear relationship between basics functions and their derivatives. Okay, let's see once carefully. See here the Price differentiation matrix. Okay, the Price differentiation matrix originates in spectral methods where here is the condition applied, where it denotes an exact linear relationship between basic functions and their derivatives. Okay, basic functions and their derivatives. By rights we should have called D1 an approximate differentiation matrix, but we sacrifice nitpicking on the altar of brevity. Okay, let's move on to the next topic, subtopic. I mean, next topic is nothing but next subtopic on skew symmetric, an order barrier for skew symmetric differentiation matrices. Okay, an order barrier for skew symmetric differentiation matrices, and here is the equation given on this slide. Okay, first point, imposing skew symmetric on results in the above are identical once we swap indices, hence they cancel. The left hand side is thus 124m of bracket of m plus 1 bracket close again open bracket into m plus 2 close bracket. Okay, 24m of m plus 1 into of m plus 2. It is easy to verify that they fail to match for all m greater than or equal to 1. Okay, they fail to match for all m greater than or equal to 1. We have proved that. Okay, we have proved that. What we have proved? They have failed to match for all m greater than 1. Next, theorem 2. The highest order of the skew symmetric differentiation matrix given by is 2.fy. Next subtopic is a third order skew symmetric differentiation matrix in a non-equidistant setting. Okay, the third order skew-symmetric differentiation matrix is a non-equidistant setting. First point, the main purpose of negative results like theorem 2 is a spur and interest in alternative settings. Okay, the most obvious manner to escape the setting of the theorem is by allowing a non-equidistant grid. Okay, by allowing non-equidistant grid. Note that here is a condition applied that in that case, strictly speaking, we venture outside the conditions of theorem 1. However, the proof of the theorem can be easily extended to non-equidistant grids, and the statement that skew symmetric in tandem with bandness leads to stability of the matrix C remains true. Let us assume that the number of grid points is even m is equals to 2n and consider a mesh. Okay, let's assume. What should we assume? That the number of grid points is even, m is equals to 2n, and consider a mesh. Okay, see, here is see the first equation given on this slide. The underlying problem in symmetric with respect to x is equals to 1 by 2 the center of interval, and we impose similar symmetric on the mesh. Okay, and here is the equation given on the screen, second equation, and what they wrote, the non-equidistant generalizing of is, and here is the equation u dash m, here is the equation, third equation. And there is what they said, where the coefficients of alpha m, beta m, k and gamma m depends upon n, the differentiation matrix. Here is the differentiation matrix. D1 is equals to 0, b1 comma 2, b1 comma 3 dots, b1 comma 2n minus 1. Next, minus b1 comma 2, 0, b2 comma 3 dots, b2 comma 2n minus 1. Vertical dots, horizontal dots, and horizontal dots, and horizontal dots, and same, it's dots. And next, minus b1 comma 2n minus 2, and next minus b2n minus 3 minus 2n minus 2, 0, then b2n minus 2 comma 2n minus 1, then last minus b1 comma 2n minus 1, 3 dots. Next one, minus b2, sorry, it's nothing but b2 is nothing but beta 2 n minus 3 minus 2n minus 1 minus beta 2 n minus 2 minus 2n minus 1, 0 is a skew symmetric by design. The order p conditions generalizing, or here is the equation. And what they said, to complete our general settings, we wish the coefficients in 4.1 to reflect the symmetric of the problem, thus we stipulate that, right? See, here is the equation. I mean, it's about lambda m values, beta m values, so and so. Next, for example, for n is equals to 4, the compound matrix is alpha mod d1 mod gamma reads. See, here is the given symmetric matrix, I mean matrix. Okay, Can we see? See, here is the given matrix. What is the elements? Alpha 1, 0, beta 1 and so and so. In this section, we do not intend to explore general schemes of this kind, just to provide a single example of a scheme of order p is equals to 3, thereby demonstrating that the barrier of theorem 2 can be breached by allowing a non-equidistant grid. To this end, we choose a parameter p belongs to 0, 1 by 2n and set. Next point, xm is equals to mp, x2n plus 1 minus m is equals to 1 minus mp, m is equals to 0. Here they said that m should be is equals to 0. I mean m is equals to 0, 1, 2, 3, so on up to n. And next point, in other words, the grid is equidistant except for a single interval. X capital N plus 1 minus x capital N is equals to 1 minus 2n p dot. In addition, we consider an equidiagonal matrix D1. Okay, what we consider in addition? We consider equidiagonal matrix D1. In other words, require that beta m, k is equals to 0 for k minus m greater than or equal to 3. Letting. Revisiting the case n is equals to 4. We have, see, here is a matrix given on this slide. What are the elements? See, this is the matrix given. Alpha 1, 0, so and so elements were given. These are the revisiting the case n is equals to 4 we have. And next point, it is fair, however, the state that this sort of brute force hit and miss approach is not an adequate methodology is designing higher order skew symmetric differentiation matrices. Clearly, much better understanding of this fairly fundamental activity approximating a derivative of an non-equidistant grid is required. And last, we came to the conclusion. Okay, number 1 is the implementation of modern high order splitting methods for the conventions diffusion equation requires a suitably accurate approximation of the first derivative by a skew symmetric matrix. In this paper, we have proved that no third order method of this kind is possible on the equidistant grid. The meaning of this is nothing but in this we have proved that no third order method of this kind is possible on a equidistant grid. Okay, no third order methods is not possible on which? On equidistant grid. That's it. And next point, once non-equidistant grids are allowed, finite difference methods of modestly higher orders can be constructed. However, the current state of the art leaves a great deal to be desired, and considerably more effort is required to obtain high order finite difference based differentiation matrices in a form amenable to efficient computation. Okay, see, here is the above graph given on this slide. Can we see? Yes. This is the graphs given on the slide. Matrices in the periodic boundary case. Okay. Matrices in the periodic boundary case. This is no longer true once the boundary conditions are directed. Okay. In that case, on which case, when the boundary conditions are directed, in that case, ongoing research demonstrates that while it is possible to choose a basis for L2 of -1, 1, which yields a skew symmetric differentiation matrix. Okay, skew symmetric differentiation matrix. It is not yet possible to compute fast and efficiently in that basis, thereby inheriting the wider benefits of a spectral method. Okay, viral benefits of a spectral method. This clearly is an issue deserving of much further research. Okay, at last, thank you one and all.